Okay, well, this is the spectrometer, and just wanted to explain the parts to it. They're all explained in your write-up, but anyway, we'll go through that. So the light comes in here, so we'll have a mercury light here, and it will be set up like this on a little platform that you're going to adjust, and you'll need to move it kind of back and forth and look with it lined up like this. You want to look through the eyepiece and adjust this until you see the brightest slit light, and then you don't want to move that. Sometimes that gets bumped, or this gets bumped, and you have to come back and check and make sure it's lined up, and the light is actually going through the slit and going through this slit and so forth. So you might want to check that occasionally. It's easy to bump. So this is basically a short focus telescope. It's a collimating telescope, and it takes light and it focuses the image of the light to the center of this platform. And that will be all set up for you, so don't twiddle this knob. In fact, don't twiddle any knobs, but this knob and this knob, I think, in the whole experiment. Everything else will be set up for you. So you may need to make a slight adjustment to the focus of this, depending on different eyes have different sensitivities. So you can turn this slightly a little bit, move this telescope in and out to focus it, because this telescope is focused on from a light coming from a distant source, or from a source focused on lighting up the center of this platform. This telescope is another short focus telescope set up to focus on the center of the platform. So everything happens at the very center of this platform where these two white lines meet. Again, this is the focus. When you do the experiment, I would recommend that one person in the group be the official looker, and the other person kind of look in there once in a while and see what's going on, because different things are going to be going on. But that way you don't have to keep changing the focus on this. So that's really all it is. These two adjustments here. This is the measuring arm lock, and let me loosen this. This is when this is tightened, and again, I'm not tightening that very tight. This is then the sort of the fine angular adjustment. So loosen this if you want to move the arm back and forth. If you want to make a measurement, you're near where you want to go, snug that down, and then move this, and it moves very, very slightly angularly. The purpose of the spectroscope or spectrometer is to measure the angular position of things, obviously different angles. An angle is the difference between two angular positions. We'll kind of talk about that some more as we go on. We want to first measure what I call a straight through or undeviated angle, which should be around 180 degrees. The example in your handout is 180 degrees in 3 minutes. And we have a close-up of that vernier setup as to how to read that, and an explanation in the write-up also. So when these two are lined up sort of straight across from each other, it will read about 180 degrees. We have a vernier scale, which there's instructions and pictures for in the write-up, reminding you how to read a vernier scale. This is a vernier scale, a 60 vernier scale, because there's 60 minutes in 1 degree, and so we'll need to measure to the nearest minute of 1 degree, which is how accurate this apparatus is. So when you take a measurement 2 or 3 times and you think you got it exactly right the same time every time, there should be no variation more than about 1 minute from those 3 measurements. So if you, again, you always want to measure everything at least 3 times. That's easy to do on this equipment. You just, if you're in position, you need to lock it, adjust this, take your measurement on the vernier scale, and then twiddle the fine adjustment knob, and center the crosshairs, which are generally not necessarily vertical and horizontal, but they're crossed. The intersection of the crosshairs is where you want to look for every time, and you need to adjust it, put that intersection of the crosshairs back and on the middle of the slit image, and that's what you want to read. Whatever you're looking for, that's what you want to read. So In the first experiment, we're going to do two things. We're going to put the prism up this way, almost exactly in the center, just a little bit that way of center. And we're going to go searching for the reflected light over here and the reflected light over here. And if you read the write-up, you see that the reflected light over here and here, by the law of reflection, which we'll talk about in just a minute, will give you that this angle between this position and this position, the left position and the right position, whatever you want to call it, is exactly double the apex angle. And you can see from this prism that it is an equilateral prism, and so the apex angle is going to be really close to 60 degrees. It'll be whatever you get it to be. It may be 60, a little bit more than 60, 60 degrees in a minute or 2 minutes, or 59 degrees in 59 or 58 minutes, whatever. But use the measurement that you get instead of just plain 60 degrees. Okay, so that's the first. After you get the straight through direction, which is your reference angle, which would be pretty close to 180. We'll try to make it close to 180 for everybody's spectrometer. And then we want to look at the reflected light on both sides. The angle between those two positions is roughly 120 degrees, giving you a 60 degree prism angle, which you're going to need in the calculations later on. The next experiment is to not only reflect the light, but to refract the light, which means the light's going to go through this prism. So when you put the prism a little past center like this, the light's going to go into the prism. It's just a thin strip of light. It's going to go into the prism, and it's going to come out the other side, but it's not going to come out the other side at 180 degrees because of the law of reflection. So we're going to set the prism a little bit at an angle like this, and again, there's a picture in the book, in the write-up for where to set that. And you will see that what happens now is the prism has, because of the law of refraction, which I want to go over in a minute also, is going to kink the light. I think that's a better word than bend, but it's going to kink the light off to this direction. And what you're looking for in that part of the experiment is where the position of this measuring telescope is relative to your original 180 degrees-ish straight through direction. So this angle here is what's called the angle of deviation, which is the angle that the beam is deviated by this prism. Now, we'll talk about why that's so interesting and important a little bit later. So the last part of the experiment involves a different concept entirely called diffraction. And this grating here, which I've slipped into the grating holder, is a diffraction grating. And this particular grating has, according to the manufacturer, this is a cheapy grating. It has about 750 lines equally spaced per millimeter, not centimeter, millimeter, scratched on a piece of plastic. And each one of those lines acts like a slit. So this is like a multiple hundreds of thousands of slits, parallel slits, instead of just the one slit we have here. And it's a little more complicated theoretically, but when you bolt this down on the platform here, we'll have some screws to bolt that down with. Then you'll also be doing the same thing. You'll be looking for where the light is diffracted, not refracted, but diffracted over here. And also you want to look at it because it's actually diffracted in both directions. And again, this angle from here to here is twice the angle of diffraction. So you can take the average of those two values and find out, or you can just take the difference between those two positions and divide that by 2. That's your diffraction angle. Okay, so that's how the equipment works roughly, and I want to talk about the theory behind all this now. So when you use the spectrometer, I mentioned in the write-up several times, but I want to say it again, do not tighten anything very tight. Just snug it down. You might have to snug it down just a little bit more to get the fine adjusting knob to work when you tighten the positioning. Now when you tighten this, you might have to tighten it a little bit tighter to get this to actually move the telescope finally in the right direction. So, okay, so the law of reflection. We use the law of reflection to find out when the light strikes this prism where it's reflected off of this surface and the other surface. And we talked about how that's twice the apex angle, which is what we're looking for. What is the apex angle? It clearly looks like about 60 degrees, but you want to measure it exactly. Okay, so let's just talk about not a prism, but a flat mirror. So the law of reflection says that the angle of incidence, and by the way, these angles are measured from the normal. The angle of incidence, here it comes. This is the angle of incidence. We'll call it theta sub I. So this is a beam of light coming in, and it bounces off this. This is called specular reflection, which means it's a smooth surface, even compared to the wavelength of light, which is pretty small. This bounces off at another angle. We'll call it the angle of reflection. And these two angles are equal. You use this every day when you look in the mirror because you can depend on this as being always the case. It depends on light traveling in a straight line, which is what you So again, these angles are measured from the normal, not from the surface, but they're equal. Of course, these angles are equal because those angles are equal. But these angles are measured from the normal. So this is a ray of light bouncing specularly off of a smooth surface, such as the prism. So, but in the prism, in the case of the prism, here's the equilateral prism. You have a beam of light coming in. Well, I'll make it kind of thicker because it's not a thin beam of light. It's a slit. Some of that light bounces off of this side, and some of that light bounces off of that side. And it's really important. I won't draw the big platform that prism is sitting on, but this is the center of the platform right here. And you want to put the prism a little bit past center so that indeed this fine strip of light, part of it bounces off this way, part of it bounces off that way. That's why I say on the write-up, make sure you see it on both sides. So if the prism's too far over this way, you're only going to get this reflection. If the prism's too far over this way, you're only going to get that reflection. So you may have to play with it to get it centered better. But then you want to make sure you see that reflection and that reflection before you measure this angle, which is 2 times the apex angle, 120 degrees. So that's the first part of the lab. It uses the law of reflection. There's a little more to it than that, and I'll let you talk about that in class. The next geometrical optical phenomenon that we're going to deal with. So here's your big prism, and you measure that to be roughly 60 degrees. You're going to set this prism on the platform at a little bit of an angle. This is more or less where the incoming light is coming in, but you want to set this a little bit of an angle so that the beam of light is coming in here. This is your beam of light coming through the slit, and then it goes into this glass prism. Now, let me just talk about this surface here. So I'll just say, here's a surface, this is glass, this is the surface here. So the light's coming in, and of course, just like it was for the law of reflection, this is the incident angle, which again is measured from the normal. And what happens when the light goes into a transparent material, and I'm talking about light as an example of electromagnetic waves, so other electromagnetic waves do the same thing. If this is air and this is glass, what happens is the beam of light, and you probably notice this is sort of the broken or the bent straw problem, or the broken or the bent ore problem. If you ever put an ore in water, or you've tried to do spear fishing, you know there's a problem there of the fact that you think the fish is there and oh, it's over here. And that's because of the law of refraction. So here the light is refracted, and this angle here is the angle of refraction, we'll use theta sub r anyway, r for reflection or refraction, I guess. And the beam here is kinked. I can, a better word is kinked there. It's right at that intersection of the surface. It's kinked and bends towards the normal. And how do you know that? Well, it has to do with Snell's law. Snell's law says this: the sine of the incident angle divided by the sine of the refracted angle is equal to something to do with the quality of air and the quality of glass. That's called the index of refraction. Okay, so for air, n is essentially 1. For a vacuum, n is essentially 1. Air is about as close as we can get to a vacuum in terms of density, and the density of anything else that's transparent, plastic or glass or diamonds or whatever that's transparent, the density of, or the index of refraction for everything else is greater than 1. Now, the index of refraction is defined in your write-up as the speed of light in a vacuum divided by the speed of light in the material. Okay, that's the speed of light in a vacuum divided by the speed of light in the material. Now, I just said a minute ago that light travels, the index of refraction is greater in any material compared to a vacuum or air. And so that means the speed of light is, because this number is bigger than this number is bigger than this number, the speed of light in a material is slower than the speed of light in a vacuum or in air. So for instance, if something has an index of refraction of 2, that means this ratio is 2, and speed of light in a vacuum divided by the speed of light in material is 2, which means that the speed of light in material is half of that what it is, which it is in air, basically. So diamond has an index of refraction of 2.2, I think. It's pretty it's pretty sparkly, as you know, and the reason it's pretty sparkly is because it refracts light more vigorously to a greater extent than glass, even, or most other things, and so it sparkles due to what you'll probably talk about in class is total internal reflection. So, pay big money for that. So we're looking for the index of refraction of the glass. Indexes of refraction of glass run from about 1.5 to 1.8. As I said, diamond is something like 2.2 or 2.4. It's one of the more, we call it optically dense materials around that are transparent. Okay, so we're looking for the index of refraction. Now, that's not all we're looking for. We're looking for two things at the same time. We're looking for the index of refraction of this light because of this prism, because of going through the prism, and we're also looking for it because different colors of light have slightly different indexes of refraction. So when you follow the path of the light through, depends on the color as to where it's going to come out. So let me apply the law of refraction there, which means this angle's bigger than this angle, which means it's going to refract, or kink, I guess you might say, this way. So this angle is smaller than this angle. We just talked about that. And so it's going to be deviated from its incoming position, it's like 180-degree position, by a certain amount. So now it's because this line, because it's a prism, and this normal here and this normal here are not in the same direction, when it comes out of the prism into air, this is glass and this is air. When it comes out of the prism into air, it's refracted away from the normal, because now we have a number up here that's the number upstairs is smaller than the number downstairs. So this angle is smaller than this angle, or this angle is bigger than that angle. That's the one we're looking for. So it's the angle of refraction. So this is the light that's doubly refracted as it comes through the prism. It's refracted here towards the normal. It's refracted here away from the normal. for the reason that we just talked about. And so the light's going to come out, instead of going to roughly 180 degrees, it's going to be deviated. So big D is the angle of deviation. And so we know it's going to be deviated because this density, this index refraction is different from air. It's going to be deviated, and how much it's deviated depends on Snell's law applied here and then applied here. It's a little complicated. We're not going to go through all the complicated calculations there. We're just going to measure the angle of deviation. There's a formula, I think it's formula number 2 in your write-up, that gives you the relationship between the index refraction of the glass and the angle of deviation, a special angle of deviation. Okay, so that's the picture. The light is going to be deviated by the prism. That's the bottom line. So let's take a look at a concept called dispersion. Dispersion. That means the index refraction for different colors of light, as I mentioned earlier, is a little bit different. Just a little bit different. Okay, so let's start over again with a beam of white light, which is basically what we have. It looks white, but it's more complicated than that. So here comes the light, and it's refracted, and it's refracted again, just like we talked about a minute ago. And this is white light, which basically means it's got all the different colors. Our white light doesn't have all the different colors. It's got pretty much very bright yellow and green and blue colors coming from this. It's a modern physics thing. This is due to electronic transitions between the different excited states of mercury and whatever other gases are in here. Unfortunately, this is not pure mercury. There are some other gases like neon or krypton or whatever noble gases that do the same thing and produce different colors. In fact, you know, neon lights are generally red, and so there's a red color, a big red color, and you kind of ignore that. We're looking for yellow, green, and blue. You'll also see, if your eyes are sensitive to a little bit of ultraviolet, you'll also see a purple line here, and you'll see a bunch of other blurry lines between these lines. So in theory, if we only had a pure mercury light, we would see a yellow line and a green line and a blue line coming out here, 3 separate lines, because the index refraction is a little bit different for yellow and green and blue. So this would be the yellow line, and the green line would be just, I'm exaggerating, be slightly separated, and the blue line would be more separated. So this is what we're looking for, because it will happen. Yes, there's other Schmiery lines besides these yellow and green and blue lines, but we're just going to concentrate on the yellow and the green and the blue lines. So then what you're going to do is take your spectrometer, and as you know how to use it, we're going to move it over. Here is your measuring telescope. We're going to move it over here and park on the slits, the crosshairs, on the yellow line, and subsequently the green line and the blue line, and measure this angle of deviation from the straight through direction. It's going to be 45, 50 degrees-ish, this angle. Okay, but because this phenomenon of dispersion, the rays, even though they come together in unison here, are separated by their different colors when they go through the prism, which is again called dispersion. And these are the colors we're looking for, and ignore all that other blurry mess around them. Okay, so we're looking for the angle of deviation, but we're not looking for just the angle of deviation, 3 of them. We're looking for what's called the minimum angle of deviation. Okay, so this prism is on a platform, big platform, and what you're going to do to find the minimum angle of deviation is grab a hold of this platform, not the prism, grab a hold of the platform, You can see it here. We'll grab a hold of the platform, put the prism on, light's coming in, it's going to be refracted. We're going to look around here for the yellow and the green and the blue lines, and when we find the yellow line, this is kind of hard to describe. You've got to see it to believe it, as they say, and I hope you will see it. So the prism's going to be at a little bit of an angle here like this, as I show in the write-up where to set it, how to set it, and it's going to refract the light over this way. And you're going to be looking for the yellow and the green and the blue light coming out there. There is a minimum angle of deviation, which is the angle by which, so here's the prism, here's the light, here's the deviation, here's the angle of deviation. You're going to have your telescope over here looking for the yellow line, for instance, to begin with, and we're going to take this platform and kind of rotate the prism and keep an eye on it at the same time. So we want to move this back and forth as we rotate this and keep an eye on that yellow line and see where it goes. Snell's law basically is applicable here, and Snell's law gives you a different answer for different angles. Makes sense. And so it's our signs of different angles, but we're not getting involved with that. We're trying to find the minimum angle of deviation. What does that mean? That means the angle that's closest to the 180 degree, roughly, line that you had to start with as a reference. So when you rotate this and you kind of follow the yellow line, sounds like a movie, follow the yellow line, and as you rotate this and this together, you kind of have to do that your own, with one arm move this, and with the other hand rotate this and follow that line till the yellow line goes as far towards the 180 degree position as possible, and that's what you want. Then you lock your measuring telescope and zero in again on the crosshairs, put the crosshairs in the middle of the yellow line, and then the green line and the blue line. And again, you want to do this 3 times to get an average. You should get an answer that's only a minute or 2 different each time you try that. So make sure you get some good numbers in doing that. So we're going to take the angle of minimum deviation and figure out from it what the index of refraction is for each different color of light, which is going to be only slightly different. So as I say in the write-up, it's going to be like 1.58 or 587 or something. I'm just making a number up. Make sure you carry it out, your calculations out to the thousandth decimal place, because the difference is way out here and not up in here. It's going to be 5.8 something, 5.8 something, 5.9 something maybe for the different colors. So make sure you carry it out to the 3rd decimal place in your calculations for n. You can round it off later, but carry it out that much far to begin with. Okay, so you're going to take your prism. When you find the yellow light with your measuring telescope, you're going to rotate the prism a little bit, and as you rotate the prism, follow around and follow that yellow line until it goes as far towards the 180 degree position as possible. And it will do that. It will actually change directions on you. If you rotate this and you keep rotating it, your line will go this way and it'll come back this way. And you want the position where it goes closest to the 180 degree mark. After you rotate this, zero in on it. When you think you've gotten there, lock this and give this a little wiggle and make sure that, yes, the yellow light is as far this way as possible, and then you want to park on that position and measure it. The difference between that and your roughly 180 degree is the angle of deviation. Not that position, that's a position. An angle is the difference between this angular position and the straight through angular position. So that's an angle. Okay, so you're going to get slightly different answers, and they're going to be somewhere around 1.5, 1.6, 1.8, whatever. It depends on the quality of the density, the optical density of the piece of glass that's made out of. I think these are somewhere around 1.6 if I remember right. So that's, and I have a whole entirely other story to tell you now, and that's the concept of diffraction. Lots of stuff that begins with D's in this lab. Okay, diffraction. Diffraction, you can say roughly is multiple, is a multiple effect. So what do I mean by that? Well, here is a diffraction grating. Let me get it out for you. One of the ones you're going to be using. Here is a diffraction grating. And you may be able to see, if I kind of wiggle this around, you may be able to see kind of a rainbowy effect of this diffraction grating. You may have seen this on a CD. I suspect you have. If you looked at a CD going around, you'll see that when it reflects the light seems to be broken into different colors. So that's kind of interesting. That's a diffraction effect. Okay, so what that piece of plastic is, let me draw you a cross-section of that piece of plastic. This is the piece of plastic, this is the bottom of the piece of plastic, this is the top of the piece of plastic, and here's what they've done to make these. That one says it's 750 equally spaced lines per millimeter. The wavelength of light is very small, and so we have to have lots of lines in a millimeter to help find it. So what this is a diffraction grating that looks like this. If you've seen the grooves of a record or seen the surface of a CD, there's not really grooves on it, but you will see when you reflect it off the light, you'll see there are things that are very close together, such as the grating here, that do this, make this diffraction effect. So this is 750 lines per millimeter. So I haven't drawn it to scale, to say the least. So each one of these lines acts like a slit, such as the slit that's on here. So there's a slit here. I'm going to draw the slits with a black marker. So there's a slit here, there's a slit here, there's a slit here. So there's multiple, there's hundreds, thousands, maybe tens of thousands of slits or lines which cause this diffraction effect. And it's a little bit involved, and I don't want to go here until you've done that in class, if you get to that class. But the diffraction effect is overall, sort of macroscopically, going to give you the same result as that prism. So if you have white light coming in and you have one of these diffraction gratings, what it's going to do is it's going to not reflect, not refract, but diffract the light. And if you have your measuring telescope over here, it's going to diffract the light. Different colors are going to, just like the prism, are going to be diffracted at different angles. So, for instance, that might be the yellow light, and that might be the green light, and that might be the blue light. Oh, I got these backwards. So, this is an angular position measuring device, the spectrometer, and so you're going to measure this angle and this angle and this angle. You don't have to do any fiddling, you don't have to wiggle this thing around, you just put it on, let the light go through it, and you go looking for the yellow and the green and the blue line, and you'll see the yellow and the green and the blue line over here also. So this angle here, which should be the same as that angle there for the same color, is the angle you're looking for. So if you measure from here to here, such as you did with the reflected light in the first part of the experiment, you'll get twice that angle. So that's the angle you want. And the formula here for figuring out how that angle is related to the color is as follows. You'll see that an awful lot in optics, the formulas that look very much like that. M is called the order number, has nothing to do with going to McDonald's. The first set of yellow, green, and blue lines you see off to the side either way is called the first order. And if you look farther out here, you might even be able to see them, you'll see another set of lines, yellow, green, and blue lines. That would be the second order. We're just going to have m equals 1. We're just going to look at the first order to the left and to the right. It's going to be like 15, 20, 30 degrees, something like that, to the left and to the right from your 180 degree reference point, right? So sine theta is the sine of this angle. Okay, this is an angular measuring device, so you get the angle, and all you have to do is calculate the sine. So we got that covered, and D is the spacing between consecutive lines on that grating. Now, if there's 750 lines per millimeter, the spacing is 1 over 750 millimeters apart. Okay, and of course we want to convert that to meters, so it's 1 over 750 with 3 more zeros, meters apart. So this value is the value of D, which is, you see, an incredibly small number. Now, the reason for that is the wavelength of light ranges from 400 nanometers to about 700 nanometers. If you want to put that in micrometers, these are 10 to the minus 9, so it would be 0.4 to 0.7 micrometers. Well, if you flip this number over, you're getting into the micrometer territory, which is why we have so many lines. We need to get into the micrometer territory. Generally, people in spectroscopy talk about nanometers because those are nice numbers. We don't like decimal points if we can avoid them. So we're looking for these wavelengths, and they're going to be somewhere in that range. You know, yellow light is over here, blue light is over here, everything else is in between. So you measure the angle with your angular measuring device or your angular position measuring device. Again, if you take this angle and this angular position and subtract them and divide by 2, you get this angle, which is the smart way to do it. Again, make sure you get pretty similar readings here for these measurements. And it's going to be something on, this is 4/10 of a millionth of a meter. This is 7/10 of a millionth of a meter. And that's how big the wavelength, that's how small the wavelength of light is. So this is always 1. This is what you're looking for. This is this number, which is a teeny tiny number, and you get the angle from the spectrometer. Okay, so want to do this for, we're going to kind of do this one way and the other. So m lambda equals d sine theta. That's the formula. M is always going to be 1. And so we can, and of course, we're going to measure sine theta. So we can either find lambda from this formula if we know d. And here I'm assuming we know d because it's supposedly 750 lines per millimeter inverted like this, a teeny tiny number. Or we can say we know d and find the wavelength. So I want you to go both ways with this. Take one of those gratings and use the wavelengths that we give you are the true wavelengths for yellow and green and blue, and find the spacing between in consecutive lines, or how many lines are there per millimeter or centimeter, millimeter. Better keep with millimeters. And on the other grating, I want you to go say you know that, and you're looking for this. So just to kind of play with this formula, one way or the other. Okay, that's the experiment. It sounds kind of complicated. It doesn't really take too long to do. It's hard to show you because we have to get the camera to look through the microscope or the telescope, which is very tricky. So you'll have to do that part yourself and see what you see. So I just wanted to mention this equation, which is a little bit nasty looking, for calculating the index refraction of the glass for different colors, the yellow and the green and the blue. So everything's the same here except for your minimum angle of deviation, which you measure carefully in the experiment, which is slightly different for yellow and green and blue. A over 2, A is about 60, so A over 2 is about 30 degrees. This is 30 degrees, and that minimum angle, again, the angle is I'm just making it 180, and this angle here. So maybe it's 140 degrees, we'll say. So the angle here is 40 degrees. That's the angle you want over there. Not the position, but the actual deviated angle from your straight through, roughly 180 degree direction. So it's going to be in the 40-ish degree range. So again, if that's 40 and that's 60, 40 plus 60 is 100 divided by 2. That's a sine of 50 degrees upstairs. This is a sine of 30 degrees downstairs. The sine of 50 degrees is bigger than the sine of 30 degrees, and hence the index of refraction is bigger than 1, as we expected. So it should give you around 1.5, 1.6, something like that. So don't forget, it's this angle, that's the angle. These are angular positions, that's what the spectroscope measures. And we want the angle, which is the difference between two angular positions. Okay.